My name's Ian Smith. I work in the marketing team here at MIPI, and I welcome you to this double header webinar. So there's going to be two parts to today's session. Firstly, we're going to have Ariel Lasry talk about using MIPI display specifications to meet the growing bandwidth and safety requirements of next generation automotive displays. And in our second part, Nadav Bannett will be talking about how MIPI protocol adaptation layers enable MIPI high level protocols over automotive in-vehicle networks. Just introduce our two expert speakers for today. So we have Ariel Lasry, Director of Technical Standards at Qualcomm. More importantly today, Ariel is representing MIPI in his capacity as lead of the MIPI Display Services Extension subgroup. And Ariel covers many roles inside the MIPI working groups. He's also a member of the MIPI camera working groups and many other roles related to MIPI A-PHY. We also have Nadav Bannett, Director of System Architecture at Valens. Nadav is going to talk about the protocol adaptation layers in his capacity as lead of the MIPI camera and display protocol adaptation layer subgroups. We're double-headed today, so we'll have part one, part two presentations, followed by that Q&A session. Without further ado, I'm going to hand over to our first speaker, Ariel, to take us through MIPI display. Thank you.
Yeah, thank you, Ian, and good day, everybody, wherever you are in the world. So I'm going to skip my introduction, as Ian has done. Today, I will mainly talk about MIPI display specification for automotive, and particularly about the MIPI display service extension DSE. That has been released recently as version 1.1. Before addressing the display topic, just a word about MAS, which is a MIPI Automotive SCADA solution. That is a framework for integrating sensors and display with end-to-end functional safety and security built in to the system. So basically, in a car, we can have a large number of sensors that can be a camera, radar, lidar, all around the place in the car, and they are connected via long reach PHY or SERDES. In that case, we have under the MIPI MAS framework or the MIPI A-PHY, which is a very robust PHY. And next day, I think tomorrow, we will have more presentation about that. And on the other side, we have also the MIPI displays, which are also in the car. They are more distributed inside the car, but still they are not all inside a single ECU, so they are distributed inside the cabin. We'll show some example, and they also need high-speed, long-reach PHY. And with MAS, what we try to provide is a full solution for sensor displays in a car using A-PHY as a physical layer, as either integrated within the sensor or within the display module, or by use of bridges, SERDES bridges, to extend the reach of the native camera and display interfaces. Yeah. This is the MAS stack diagram, which kind of represent all the different specification we have in MAS. On the bottom part, we have the automotive long reach PHY, A-PHY with the A-PHY electrical, physical layer, and the data link layer. And then going up the stack, we have the adaptation layers, and we have adaptation layer for camera, for display, with different type of adaptation, either for MIPI or VESA display, and also a number of other adaptation layer for additional interface that we need to use along with the main MIPI camera or MIPI display interface. And above this adaptation layer, we have the MIPI protocol, which have been already proven in billions of devices in the mobile with CSI, DSI, and we also support VESA DisplayPort here for the A5 framework. And above the protocol, we have the so-called service extension, which provide additional service for end-to-end functional safety and security, but also content protection and other functionality. So today we are going to focus on the MIPI display and have a bit some talk about the VESA display because this is related. So that's an example of automotive cockpit display where we can see a number of displays here going from the left to the right with a left side mirror display, also the right side mirror display, driver instrument display, information, center information display, lower console display, and also a co-driver display. This is just an example. And on the right side, I put some example of what could be a display size and what kind of display resolution can be used. So you see, there are a whole number of displays of all shape and resolution and sizes distributed in the car. And what is MAS doing for that and how we address that? So one very interesting topology that we use for the display is daisy chain topology, and I will show the diagram later. So in principle, the daisy chain structure is like that you have one ECU, like here on the left side. It has a link to the first bridge number 1, which is talking to the display. And then on the link to the bridge number 1, all the image data, the pixel data and the control data to all the display, in this example, 4 display in the chain, are communicated on link 1. And the bridge 1 take only the data for display 1 and given to display 1, and forward all the other data for the other display to the next link, and so on. So in this example, we can see a daisy chain with 4 links, and we can support at the same side on the same cable with high-speed downlink on the A5 up to 64 gigabit per second, all the, let's say, the pixel data, which are going downlink. And on the uplink, we have a lower speed uplink. 100 megabit per second is fully sufficient to provide control and status data from the display to the ECU. And how we apply that in the car, so looking at the diagram, the picture we had before, so this is an example of how to use daisy chain in a car, where you have the central ECU here with the link 1, link 2, link 3, with a free display in the daisy chain in this example. And there are maybe some other daisy chain here, and also some point-to-point. But what I wanted to show here is that, yeah, in order to reduce the number of cable to connect to each display, this daisy chain linking is very interesting and efficient, but it requires on the link number 1 to have a very high bandwidth because we need to transport the pixel of all the displays on the chain. Yeah. And now, if we are considering a different type of resolution on the display, so I made an example here with 3 types of configuration with different resolution for display 1, 2, and 3. And looking at the bandwidth that is required for the total bandwidth that we need on the first link is very high. Here we have in this simple configuration 37 gig, and we go up to almost 100 gig when we have this very large display. And this is clearly getting very difficult how to transport such a huge bandwidth. So how we can solve that with MIPI, A-PHY, and DSE and DSI to get together is that we have A-PHY with A-PHY version 1.0 and 1.1 having gear 1 to gear 5 up to 16 gigabit per second on a single lane. And from A-PHY 1.1, we can have a dual lane, so it can go up to 32 gig. And now we are finalizing the A-PHY 2.0. We will have gear 6 and gear 7 bringing up to 32 gigabit per second on one link. If we have a dual lane, we can have 64 gig. And so if we have such kind of configuration, let's say that this is the highest resolution configuration, we can see that if we are not using compression, this is DSC's display stream compression, yeah, there's almost there's no way to transport all the pixel data. But when using compression, we can reduce the full required bandwidth from 96.5 to 32.2 here, and we can see, oh, we can map it here to dual lane gear 6 or to gear 6 on link 2 and gear 4 on link 3 in configuration 3. And if we are in configuration 1, yeah, we can use higher speed A-PHY gear on link 2 and gear 3. In this example, when it's uncompressed, but when it's compressed, we can even further reduce the overall speed link. And now, how does it work all when we are in the car and we need to guarantee end-to-end functional safety? Yeah, because end-to-end, we have really to start. One end is the ECU generating the pixel data on one end, and the other end can be the display at the last end of the daisy chain or somewhere middle of the daisy chain. When we have all these different links and introducing compression. So DSE is helping there. And DSE, so DSE is the what we call the display service extension. It is extending the DSI2 protocol by adding additional new protocol, data service protocol, closer to the application layer directly above the DSI2. It provides the end-to-end functional safety protection for the data plane, pixel stream, for the transport, and also for the control plane. And it provides also some other additional service like end-to-end content protection with HDCP, IIA, timestamping, and some advanced end-to-end functional safety protection for region of interest and compressed pixel stream I was talking about. Yeah. So the basic guideline that we were using in MIPI mask and also for DSE is the ISO 26262 standard for functional safety, and particularly this Annex D of the -5 spec, adding information redundancy, frame counter, timeout monitoring, and the combination of all this to claim high diagnostic coverage. And I will show that in the next. So here we see, this is an example, this is a summary table, sorry, about what we have in DSE, data service protocol and functional safety tag mode. So we have defined two SEP tag mode and one FSET tag mode. Tag mode is it's kind of a verification tag mode to check for functional safety error. So we have two SEP tag mode and one FSET tag mode. And we have a so-called HVM tag mode, which is host verification tag mode. And we have DCCP, which is for DSE control plane protection for DCS. So in and here we can see for each of these tag mode what we are protecting exactly. So in SEP tag mode 1, this is similar to DSE 1.0. We are protecting on the granularity of per message, and the verification, the detection of error is done on the display, can be done on the display side, on the downlink, and on the SoC side on the uplink. When we're using Sepfusa tag mode 2 per frame protection, the detection is done on the display, and we're protecting everything, the pixel data, the transport, the control from SoC to display, but we don't protect in the downlink with tag mode 2. We are using tag mode 1 for the uplink. Okay. In FZ, we protect also per video frame granularity, and we also have support for both video mode and command mode protection. And we can make protection every single frame or every n number of frame there. And we can also support end-to-end protection for region of interest and compression. And I will show how we do that. But there's no support for control from the display to the SoC. And for that, we introduced the DCCP protocol that provide per block of DCS command, so DCS read and DCS write command for configuring and checking the display status. And there is a new mode which is called HVM mode, which is a host verification mode, where the detection is done by the host side only, and it can detect every N video frame. That's the granularity. If I now go to the protocols, so the service extension packet protocol, the SEP, basically what we do is we add header information like a message counter and information about the packet data type which is extended and which virtual channel it is with EVC and EDT. And we add some CRC for redundancy. And we have a message counter in a header and CRC, and we can use that for message-based protection. Yeah. And once they go to AFI, after we have the SEP are segmented to fit into AFI packets, as maybe Nadav will explain later. The other protocol is DSE is FZ over DSE, like a frame service extension data. What we do is that we protect the full frame within one frame granularity, and then we can send one single FZ message, which is coming in the vertical front port after the active frame data, that contain all the various CRC and message counter that we need for making the functional safety verification. Yeah, and here we can have different CRC for different region of interest, like I have shown here. Like maybe this is one specific region of interest, this is another one, and this is to increase the diagnostic coverage. So maybe there is a different level of handling of transmission error when we are in a very relevant safety protection specific region of interest than if it is like I will say user interface data. Yeah, that's why we protect specifically each region of interest. And now when we have compression, the biggest issue with compression is how to make end-to-end verification of the pixel data, because the pixel data have been compressed. And the compression is lossy. Yeah, so it's difficult to calculate a CRC on the original pixel data, on the uncompressed data. But we are using the VESA DSC engine for compression, DSC for display stream compression. And this engine is on the transmitter side, is calculating the reconstructed pixel to have a very low difference between the reconstructed pixel and the compressed pixel, between the reconstructed pixel and the original pixel, to determine what are the compressed pixel data. So what we do is that we make the CRC check on the reconstructed pixel. And since the engine, the compression engine is running per column, per slices, in order to reduce the number of CRC, we group all the slices into slices per column, and we calculate the CRC over one slice column, which include multiple slices belonging to one column. And when we have region of interest, we take all the slices in one column which are belonging to a specific region, and we calculate slice column RY CRC. And the method of calculation of this CRC has been aligned with the VESA DisplayPort automotive extension specification, which have also functional safety and security protection. And we have done it in such a way that the CRC of MIPI DSE will match exactly, beat exact, the CRC of VESA DisplayPort automotive extension, so that it's possible to make verification of pixel data in heterogeneous display system. That's for your reference. This is a host verification mode. I'm not going to the detail of this here. Basically, this is a new function to enable functional safety verification in legacy devices that are not supporting the new SEP or FSED protocol, because this can be run in software on the host side. So, of course, running software functional safety, what we do is that we check the CRC for a full frame, and we check a message counter, and this is calculated on both sides, on the host side and on the device side. And there are some synchronization mechanism between the host and the device to enable the verification of the CRC between the host and the device to check that is all the pixels have arrived correctly. Yeah, and timeout monitoring can be added to that. In order to enable interoperability, we define a multiple profile for DSE 1.1 because we have multiple tag mode and different capability. So what we have done is, for example, in DSE 1.0, we have only one tag mode, so there was no need for profile. But in DSI 1.1, we introduced this free tag mode. So we have two basic functional safety profile. The one which is used for a legacy device, we call it profile 0A, basically using the host verification mode. And profile 0B, which is using SEP for devices supporting SEP. And then we have an advanced profile called profile 1, which is using the FSED protocol, and it has not only the FSED protocol, but also support for region of interest. And it is very similar to the VESA Display Automotive Extension profile 2. Yeah. So as a summary for display service extension, so the DSE extend the well-proven DSI2 protocol. We add additional end-to-end functional safety protection at the application layer protocol covering both the display data, the transport, and the control. We introduce advanced functional safety protection, including support for compression and ROI. And this helps us to support larger display resolution and higher bandwidth for daisy chain topology and make advanced diagnostic. And we align the CRC with VESA DisplayPort to enable heterogeneous display system. And we introduce this new interoperability profile to enable better interoperability and design trade-off.
Okay, thank you, Ariel, for your presentation. If you do have any questions, please type them into the chat. We will take them, all the questions of the Q&A section later on. But thanks, Ariel. We'll now move to part 2 of our webinar, looking at the MIPI protocol adaptation layers. So first up, we're going to have Nadav talk about the A-PHY PALs. I think then Ariel's going to join us again just to talk about a new PAL that's under development that's specific to camera. So I'll hand over to Nadav. Thank you.
Thank you, Ian, for the introduction, and hello, everybody. So yeah, the second part topic is the protocol adaptation layer for MIPI A-PHY. We are discussing, if you remember from previous section, we are discussing this figure, and we are concentrating on a red box in the middle there, which is titled adaptation layer. So you can see if we look at it vertically, we can kind of the context is application, for example, for camera. So we have the entire set of layers to assemble this application, or as Ariel described just now, for the display application, we have this vertically. If we look horizontally on the red marked layer, this is the layer of the adaptation layers, and the purpose of that is to take the native protocol of the application and adapt it for A PHY, or represent it in A PHY language, kind of. Okay, so this is where we have, you can see that the two main protocol that we are discussing is the CSI2 and DSI2 for camera and display. We have also the PAL EDPDP for VESA DisplayPort. And on the rightmost part, we have a bunch of smaller boxes for adaptation layer, for basically for control and management protocols and interfaces like I2C, GPIO, SPI, Ethernet, etc. So this is context for our discussion right now. Let's begin with some system overview of some of the applications. So starting for sensor applications, we can see here two types of sensor, the camera sensor and the radar, which are connected to the SoC at the other side through a PHY connection. And here we can see two types of integration levels. You can see that camera and radar are kind of integrated. It means that the A PHY and the adaptation layer are integrated with the native protocols of the camera and radar. On the other side, this is an example of a non-integrated solution where we use a bridge to take the traffic from the A PHY and represent it in kind of a legacy interface and protocol to a legacy devices like the SoC, which uses for in this example C-PHY and D-PHY for the CSI and you know, native I2C and GPIO signals. Here, second example for the camera sensor kind of applications present even more, you know, extended set of adaptation layers to resolve some kind of application. In this case, we are speaking on a zonal architecture. So we have zone A that kind of aggregate all incoming sensors from kind of an array of cameras, for example, for surround view, together with some actuator and sensor that in this case uses 10BASE-T interface for their data transfer. And they are all kind of synchronized and timed with some mutual sync event coming from the SoC. So the SoC gives all of those sensors the same tick or the same sync event. So you can see that for this complete application, we are using bunch of adaptation layers, of course, the CSI to transfer the image data from the sensor to the SoC, but also the I2C to carry the CCI and the GPIO adaptation layer to carry, for example, the synchronization event, and also the Ethernet adaptation layer to carry 10BASE-T actuator and sensor information. Now going to some examples of display applications. So here again, we can see a display data coming from an SoC through a bridge. Again, this presents a non-integrated type of solution. To the other side, the far end, a display that is integrating both the API and the protocols, in this case DSI, into the TCON and the panel for a display module. Here we are using the GPIO adaptation layer to carry on the TE signal. If you are familiar a little bit with the DSI, you know that in a command mode, since in a command mode it's not frame by frame synchronization. The SOC sends a command with image data on a request from the display, and this request is carried with a TE, which is kind of a time sensitive event that carries with the PAL GPIO. And on the lower part, we have the kind of even broader application that again uses the PAL Ethernet, the Ethernet adaptation layer to carry a touch panel information coming back from the display to the SoC. In this case, we are using the display port to carry the image data from the SoC to the display. And the I2C adaptation layer is used to carry the auxiliary channel of VESA DisplayPort, again from the SoC to the display. Yeah, and the GPIO adaptation layer is used to carry HPD from the display to the SoC. And again, Ariel mentioned earlier that, this daisy chain is kind of typical in such applications. So here is an example of a daisy chain that uses the API multi-port link layer capabilities to create some kind of forwarding element in the API network. So traffic or image data will be, dropped at display 1, but the relevant information for display 2 will carry on at the API level to display 2. So this gives you some overview of possible applications. But now if we speaking on this, the horizontal level of adaptation layers, we can maybe think of things that maybe are common or challenges to any adaptation layer when we speak of that. And those are first the automotive condition and performance, because the task here is to assist or provide ways to implement applications for automotive. So in automotive, we have the EMC requirements, harsh environment, long connection typically is maybe related to zonal or centralized architecture ready. As Ariel mentioned earlier, the end-to-end protection, for example, functional safety, maybe security. It is a fixed topology, okay? Cars are made once and topology is fixed there for the entire use of the car. And it is medium scale network, so it's not like World Wide Web or of trillion of addresses and devices. It's big, but not so big. It's medium. In terms of throughput, so both in sensors and display, we are speaking of image data, which are typically high throughput demanding. And we also speaking on aggregation, both as we saw the zonal and also as Ariel mentioned, the daisy chain, probably usually calls for some kind of aggregation, which contribute to the throughput challenge. And also we have the low throughput controls and commands are usually also aggregated, creating another load, additional load on the total throughput. So throughput is a challenge. Generalization trade-off. So when we are coming to standardize and create specification of a standard, we need to consider both the trade-off between being specific, because if we specify something specific to some kind of application, it's probably going to be efficient. But if we specify it in a generic way, it maybe can serve many specific cases. So we have we need to think how to make a good standard that will serve both be efficient, but they will also provide ability to do reusing and common implementation. And we have another challenge, which is the interoperability. The system will be built from multi-vendor providers, and all product must play together. So interoperability need to be taken care of. So now let's see what are the MIPI solution or contribution to those challenges. So here, for example, on the left side, we can see the challenge. On the right, there are the relative standards from MIPI that comes to address those challenges. So for example, for automotive conditions, of course, we have the AFI standard that is a long reach, EMC resilience, integration friendly, and addressing the target network topology of automotive, both all cases that exist there. We also have the standards of CSE and DSE for end-to-end protection, including the security and profiles that assist and define and specify the end-to-end protection, both for functional safety and security. And we have the adaptation layer specification that, on those cases where, end-to-end protection is not provided, then at least we can provide a PAL-to-PAL protection, part of the specification of the standards of the adaptation layer. And for throughput challenge, so again, MIPI A5 standard is providing a multi-gigabit connection, which also deals with multi-streamings, and the adaptation layer provide efficient mapping between all of the relevant protocols that are being adapted to A5, and doing that in an efficient way, and make use of the throughput in efficient way. And also, as we mentioned before, generalization trade-off. So while designing the adaptation layer standards, there was an attempt to identify those modes that may be a trade-off to one another, and try to make modes for each one of them to get the best operation according to the preference that you are aiming for. So both be general, but still provide a specific and efficient solution according to these protocol characteristics. And in terms of interoperability, so there is a big attempt and effort in MIPI to provide means for interoperability. So both the A5 MIPI A5 compliance program is being developed in MIPI. There are CTS standards, CTS specification for each standard, like CSI, A5, of course, DSI. So each of those standards has a CTS accompanied with them. Also profiles for the security. So to, again, foster the interoperability challenge. and it's all under the same organization. So there is way of sharing information and making a complete and holistic approach to interoperability in this sense. When we are discussing non-MIPI protocols like VESA, EDP, or others, then there is an attempt by the adaptation layer to still support any legacy or native compliance program while using adaptation layers at both ends. For example, in VESA, if you build a VESA system with two bridges, then you can kind of create a branch device. This is defined in VESA specification, and a branch device have a complete CTS test that make it compliant. So still, by implementing the adaptation layer, you are not breaking the way to test your device for interoperability. Okay, this is again a view of the PAL system. So you can see this is that the layer, the adaptation layer, is here marked in a green box, and its interface between the native protocol and the A5 protocol. Here on the top right, you see the cloud of the A5 network. In the network, you see the blue circles. This represents A5 forwarding element. This is pure A5 devices, which construct the network. On the edge of the network cloud, you see the green circles. These are the adaptation layer device, any device that implements adaptation layer. And outside of the network, you see the red circle. This represents a native device. Okay, this device is not an A5 device, it's a native device. And the interesting thing is the red and green devices that you can see on the edge. These are the integrated device that implements both the legacy protocols and the A5 adaptation layer. Down here, you can see we spoke about the standard organization. When everything is under MIPI, this is kind of straightforward. When it's not, we saw a way to still provide ways of compliance testing and interoperability testing. Also mentioning the fact that part of the adaptation layer, the protocols that are carried are non-standard at all, kind of. This is, for example, GPIO or I2C or SPI, which is kind of a de facto standard. So for those, we don't have an organization or any strict CTS to adhere to, but still there was an attempt to address de facto and common usage of those and still provide a standard that will foster interoperability for any implementer. Okay, here now we can go through some of the adaptation layers and see major topics around the things or topics that we discussed. So for example, starting with the CSI, so you can see here on the middle top a figure of a network that connects several camera sensors and several SOCs that are all connected to some kind of an A5 network. So a lot of different sessions and connections are possible through the A5 addressing mechanism and networking. The efficiency of the traffic is made, for example, by selecting to tunnel image data, but not tunneling any blank information. If you're familiar, between frames or between active image data, there are a lot of kind of transmission of nothing or blanking. So these are not being transferred for efficiency. Also, protocol data are being tunneled, but PHY related symbols are not being tunneled. So to be kind of PHY agnostic adaptation layer. In terms of modes, you remember that the trade-off between being generic and being specific. So there are modes in the adaptation layers for transparent and legacy. These are, remember that the protocol, the end-to-end protection protocol can be implemented at the sensor itself following the CSE extension to CSI protocol. And if this is the case, the A-PHY, the CSI adaptation layer will not add any protection elements to the traffic. It will just transparently tunnel the information from the sensor to the SoC, and this information will be protected end to end. And this mode is called transparent. But maybe in some cases, sensors will be legacy sensors that doesn't implement the CSE protocol for protection. And in this case, the adaptation layer will add protection elements to the traffic using the same method as specified in the CSE. So a legacy device can be connected to a non-legacy new device seamlessly with the adaptation layer. Also, there is an optional timestamping and PAL-to-PAL protection, as we discussed. And there are rich native feature support for features that are supported with CSI, such as LRTE, USL, and others. Yeah, support for MIPI CSE, as we discussed, and the PAL bundle, as we discussed. Typically for camera module, apart from the CSI and image traffic, you will need to provide ways to tunnel CCI and other GPIO. For DSI, it's the same. You can see on the right top right corner the flow of image to SEP, as Ariel said, and then to A-PHY packets. Again, for efficiency, tunneling the image data and not the blanking, protocol data and not the PHY symbols, timestamping and being time sensitive. Support DSE. This is the display extension protocol for protection, and PAL bundle as presented in the lower part. Also, the PAL EDP-DP, very similar to the DSI too. So again, you can see here how a DisplayPort image is being sent with A packets over A-PHY, and the fact that each A packet is being timestamped with the SEP. So for timing and time synchronization, time sensitive. The fact that the DPAE, this is the VESA automotive extension to provide protection, is being supported, of course, by the adaptation layer. And here, this is again the PAL, the adaptation layer for Ethernet. Again, this is, you can see on the top right corner where the adaptation layer is being interfaced on the XMII interface. Again, for only data is being tunneled for efficiency, not idle, for example. Again, there is a way to timestamp all the information for accurate timing reconstruction for example, in supporting TSN. Yeah, for GPIO, again, GPIO is again a nice example of a very generic way to do everything. Okay, you don't have any restriction on the pattern of the GPIO, the rate and stuff like that. So there are two modes that provide the trade-offs. One is a continuous oversampling. This is in, to simplify, in this way, you don't need to know what happens on the native GPIO signal because you oversample it fast enough and it is being transferred to the other side. But in turn, it consumes a lot of link traffic. So for that, if you have an event or if you have a GPIO that only toggle once in a while, then you can use the event-driven or event pattern mode, and then you officially use the link throughput, but you need to somehow be to understand the changes of the native GPIO. So this is, for example, two modes that provides, give you, the right trade-off to the implementation. Again, in I2C adaptation layer, again, there are two modes. The single byte mode, this gives you a very strict control over the acknowledge of each and every byte, but in turn, it kind of depending on the round trip delay. From the other hand, if you know that you have that you have a chance to assemble few bytes, then you can work on a multi-byte mode. This mode is using the throughput of the link more efficiently, but in turn it gives you a different trade-off to your application. And of course, this adaptation layer provide PAL-to-PAL protection because because in some cases I2C does not include end-to-end protection. This is true also for the GPIO, by the way. The GPIO adaptation layer provide PAL-to-PAL protection for functional safety. Yeah, because it is not included in any known GPIO protocol. And for I2C, for example, it's a little bit different because, for example, in MIPI CCI, there is a CCI SE protocol that do use kind of protection within the protocol itself. So in this case, this protocol will enable a true end-to-end protection. But for all the other protocols that are carried over I2C, the adaptation layer can provide PAL-to-PAL protection. Yeah, this is the last example of the PAL SPI that also provide two modes for, to handle the trade-off of, again, the efficiency of throughput usage over the link versus, the amount of change that are required to support it. So there are the echo mode in which the transaction is exactly the same as the native transaction, but it is being transmitted 2 times. So it is a double or half of the throughput is available because everything is doubled, but the transaction is similar, is not changed. And the pipe mode is far more efficient in terms of link utilization, but it needs the host controller to change a little bit the way that it constructs the transaction. Also providing PAL-to-PAL protection. And yes, this is it.
Here I wear my camera work group member hat. what we are doing, and we are now defining a new protocol adaptation layer for CSI2 for transport of CSI2 over AVTP, which is a 1722 audio video transport protocol. And this will enable CSI2 transport over 802, IEEE 802 network, like for example Ethernet or Wi-Fi. And this is also using SEP, similarly to what we see in CSI2 PAL for AFI. And basically what we do there with the new 1722B spec that IEEE is working on, they are defining a so-called new generic image sensor format. And this is the interface we are using on the 1722 to transport CSI2. And in addition to that, we are using the ACF message for I2C and GBB, which are defined by 1722B, to transport all the control information of camera control interface, CCI. That's basically how we encapsulate the CSI2 to AVTP protocol. It's very similar to the SEP picture I've shown before, but this is now applied to CSI2, and we basically encapsulate, we segment the SEP into multiple AVTP packets, and each AVTP packet or AVTP ACF JSF message is then put into IEEE 802 frame. And it's possible to use the MIPI CSE for end-to-end functional safety and end-to-end security protection as an option to that. So that's an information. MIPI is working on that to enable the support of CSI2 over Ethernet and Wi-Fi network. Nadav?
The summary of key points. So MIPI is providing under the same roof a comprehensive standard coverage of plethora of protocols and interfaces that are typically used as complementary to the primary image data protocol traffic in automotive use cases. So again, we mentioned we have the CSI and DSI, maybe also DisplayPort, but we have a bunch of other standards and specification to specify how to carry other protocols for control and management of auxiliary data. This allows holistic view that enables efficiency, use of link throughput, as we mentioned, also compliancy and interoperability, end-to-end protection, which is key feature in automotive, mainly for example, for functional safety and performance, quality, robustness. For MIPI CSI transport option expanding beyond short reach, CSI and C-PHY and D-PHY to a long reach A-PHY. Sorry. Okay.
I think the last bullet was aerials, actually. So maybe aerial.
I will. Basically, we are expanding the different transport option for CSI2 beyond the short reach, C-PHY and D-PHY, also to long reach, A-PHY, CERDES type of network, but also to time-sensitive networking transported over 1722 to 802.3 wired Ethernet and 802.11 Wi-Fi wireless network connectivity, as I mentioned before. So a lot of PALs we have.
Yes, too many PALs maybe. We've overdone it. I think we've obviously overrun our session today, and we do need to wrap up. So we're going to have to curtail the Q&A. I see questions coming around AFI and kind of options for AFI going forward. We obviously have an AFI session tomorrow, so it's probably a good opportunity to submit that question into the session 4, which is the first session tomorrow. But we do need to wrap up today. I'm afraid we don't have time for Q&A. But if you do have questions, please submit them to the admin@mipi.org email address, even if you're watching on demand. We're a small team at MIPI, so your questions will get a response. If there's a need to perhaps expand any of the information today, obviously we've covered all the PALs in rapid fire succession. We could go into a lot more detail on each one. So if there's a need to perhaps develop a webinar on one of the specific PALs to go into more detail, then give us that feedback and we look to do that going forward. Obviously, you can find a lot more summary information in the introductory guide to maths, and please tune into our blog going forward. Thank you, Ariel, Nadav, for your presentations today. Really appreciate it, and thank you, audience, for listening to us. Apologies once again for overrunning, but hopefully you found the extra information interesting. Okay, thanks a lot.